Hi, my name is Michael Collins, and I'm here to talk to you today about using the Microlab visual spectrometer in order to generate displays in Microsoft Excel of wavelength versus intensity for emission, or wavelength versus absorbance for high-resolution absorption spectroscopy displays. This is the first of 3 videos. In subsequent videos, we'll be looking at how you do this with emission spectroscopy and how you do it with absorption spectroscopy. So first of all, Microlab's visual spectrometer is really unique. Most of us are familiar with spectrum tubes where you can just hold them up to the light or any light source and presumably see a spectrum, although we're never really sure, are we, what the students are actually seeing. In this case, with its unique design that includes a sample compartment between the slit and the diffraction grating, you can use these handheld spectroscopes for just pointing and shooting at the sky, pointing at any fluorescent light or whatever, but you can also use them to photograph an emission spectrum or an absorption spectrum, and then process the spectrum using shareware and spreadsheets such as Excel in order to create a graphical rendering of intensity. So that's the gist of this particular quick slideshow, is to show you what you'll need to do that and what you might expect to see when you do it. Here's the setup that I have used. First of all, if you take a look at it, you can see the visual spectrometer right in the center. Behind it you have a helium lamp with a power supply for generating the light for calibration. We also have a source of light. In this case it's a tungsten filament lamp, but it could be any source. On the back side we have a digital camera and we have a diffraction grating. So the digital camera in this case is on the Microlab accessory camera mount. You could also use a tripod, of course. This is a Canon point and shoot 12 megapixel camera. You don't need anything that fancy, but it helps to have something that you can actually mount on a on a tripod or something like that. And I also have it set up for a timed shutter, so I have a 2-second delay on the shutter, so I'm not jerking the camera around while I'm taking the picture. We have a diffraction grating for viewing or photographing the spectra on the back of the spectrometer. In this case we have the helium emission tube and a power supply and a light source. Again, this light source could be another emission tube, such as hydrogen or mercury or carbon dioxide, water vapor, whatever. It could also be a fluorescent bulb, or it could be something like a candle or a chemical reaction that emits light. Lots of possibilities there. Notice the fiber optic cable. Fiber optic cable takes the light from the helium emission tube into an adapter at the base of the slit, so that the visual field sees not only the spectrum from your emission source that you want to view, but you also see the lines from the helium spectrum that you can use in order to carry out a wavelength calibration. So you go from a qualitative spectral observation to the capability of having quantitative wavelength displays. There's a sample compartment also for liquid solutions in a 21 millimeter vial that Microlab supplies. Now, for emission spectra we don't use this. That's just for absorption spectra, so we can shine the light through the slit and watch the absorption of certain colors by the colored spectrum, by the colored sample. In this case, though, we're not going to have, for emission, we wouldn't have that. We would just put a dark cloth over this to minimize the stray light. Here's the view that you would see through the eyepiece. This is a one-shot photo. You see them both at the same time. In this case we have a mercury line, or a mercury lamp, and then down below it we have the helium lines. I like to use helium for the reference for getting the wavelength calibration because it spans the entire spectrum. You have lines all the way from the violet out to the red, and so you get a really good calibration curve with lots of degrees of freedom and a high correlation coefficient. For absorption, it's a similar setup. You still have the digital point and shoot camera. This time I've got it shown on a tripod mount. We still have the helium emission tube. We still have the fiber optic cable and adapter. But now we've moved the light away from directly in front of the slit we want a diffuse light source, so we're going to bounce that white light from the incandescent light bulb off of a piece of white printer paper so that the diffuse white light can serve as our source. And this is what you would see in absorption spectroscopy. Here we have a green food dye on top. This is the spectrum of green food dye. You can see some attenuation of the red compared to just that coming off of the white paper. There's also some attenuation out in the violet compared to coming off the white paper. And down below here we can see the helium lines, although they're kind of dim in this particular photograph. They show up pretty good visually. We can still see the lines, and the image capture software will be able to see them as well. What's really neat about the the subsequent videos, I'm going to show you how to take it from that actual spectrum to the graphical rendering of a spectrum in absorbance versus wavelength. So here we have the absorbance peak at 625 nanometers, corresponding to the absorption out in the red range of the spectrum. And here we have another absorption peak down in the violet at about 430, 440 nanometers, again corresponding to the attenuation out in the violet end of the spectrum. So we go from a visual display to a graphical rendering. Here's another example. We have potassium permanganate solution on top. This is the absorption spectrum. Here we've got the white light spectrum in the background, and you can see again virtually no attenuation in the orange, red, yellow range of the spectrum, no attenuation in the violet end, but we do have a series of dark and light bands with some attenuation in the kind of the blue and the green. Okay, and again down below here we have the helium emission line. Now if we convert this to a graphical rendering, we get the absorption spectrum of potassium permanganate. This is fairly familiar to most inorganic chemists. Actually, it's remarkably similar to what you would get from the same solution going into a Hewlett-Packard 8453 diode array spectrometer. This is the one on the bottom here shows a 10 millimeter light path. The one on the top is a 21 millimeter light path, the vial that goes into the spectrometer. Notice the absorbance maximum is roughly double. We go from about 0.45 to about 0.9, and so we're similar not just in shape but in the actual absorbance values, and that is remarkable, and actually it was unexpected, but we are able to do this reproducibly. The equipment that you need is fairly simple. Excuse me. You'll need a PC or a Mac running Excel and a software package that's free from the National Institute of Health called ImageJ, originally developed for scanning gels from electrophoresis. We're using it to scan photographs of spectral output. You have a visual spectrometer, obviously. You can get the fiber optic cable and the adapter from Microlab. You need a digital camera and a means to load the photos onto the PC, a USB connector or some kind of SD card. Of course, it would be, yeah, you're gonna, well, okay. A helium lamp source, power supply for wavelength calibration. Of course, you could use other lamp sources. Again, I like the helium because of the number of lines that it has. Gives you good, reliable wavelength calibration. You'll need a tungsten filament lamp source for white light and absorbance spectra. You'll need other emission sources for emission spectra. And you'll need some kind of absorbing solutions to demonstrate absorption. Different colored food dyes work great, or different colored transition metal salt solutions. That's it. So take a look at the other slideshows and the other films and or videos and get a chance to try it yourself, converting photographs into emission spectra.